the perfect morning because I'm continuing Stefan's work and talk about more Apple fail. It's funny because I'm reaching the same conclusion as Stefan, as you will see. Who am I? Most of you already know me. I've been presenting since 2 years ago. I was really happy to come to SyScan when I was selected because I was going to say, I'm not anymore a white hat. Unfortunately, things changed and I'm going to be again a white hat. Ooh, again, you know. I have the really bad habit of creating too many slides, as you are going to see. This talk is 171 slides. You'll excuse me, I have to skip some stuff. You know that not even whiskey can stop me from talking too much, which is funny. So let's start. What is this talk about? I'm going to show you how to load kernel rootkits in macOS, bypassing the code signing feature, which is a new protection on the latest OS X, and bypassing the kernel interfaces. So you don't need to use anything from the operating system. You just need to use some vulnerabilities. It will be your own conclusion if the bugs that I'm talking are backdoors or not. I will exploit some design and implementation flaws. I will exploit some unpatched kernel vulnerabilities. And I will, the latest one and the most beautiful one and the one that I really regret talking about, OS X feature that is really great for loading rootkits. Assumptions. You know me, I'm an economist, so I like to explain the assumptions. This is a post-exploitation talk, so it assumes that you have root on an operating system, on OS X. I'm not an exploiter, or I'm not many exploiter. I prefer rootkits and low-level stuff, so let's assume that you have root. I have this question: what do you estimate the probability of getting root in OS X? We can discuss this as we have seen with the first talk in SyScan. The probability is probably high. I don't believe anything below that is true. For example, Ian Beer has shown us his great work. You have like this amount of vulnerabilities that he found like in a couple of months as he released the exploits for a few of these. You get funny stuff. For example, vulnerabilities are patched in iOS. In OS X, they are not patched, so it's a mess. You have these exploits, one of his exploits that works on Mavericks. The funny thing is that this exploit wasn't patched in the latest security update. Apple patched a ton of vulnerabilities. They released the same patches for Mavericks, but this exploit still works, which is funny because you are patching a bug that has a public exploit that works. It's very reliable, and it still works on the latest version. Another presenter, Trimo, that shows us how bad it is to install foreign software on your Windows machine. He has a remote code execution on Safari on the latest version. He tested with all the latest updates. It still works. If you want to see his video, you have the link. So as you can see, there's no lack of exploits in macOS. And there are much easier alternatives in OS X. You just need to ask the user, please give me admin. You have this bot, iWorm. It infected 17K hosts or more or less just by asking the users. Please insert your admin user and password, and then you can do whatever you want. More interesting vectors. You have many installers and updates being delivered over HTTP. Even Apple stuff is over HTTP. They have some code signing stuff and so on. But you have so much software that asks for admin privileges being delivered over HTTP. So if you are in the network, you can intercept this, modify, and do whatever you want. You have also many applications installed with wrong permissions. There was the talk at CanSecWest last week about the dynamic libraries attacks. I have known this attack for a while. I talked about it in ITCon 2 years ago. You have many applications with wrong permissions. You can do whatever you want. Many of those apps have privilege helpers that will ask for admin password. You just need to replace a binary, wait for the user to put the password, and then do whatever you want. So my conclusion is the attack surface is big. Getting root on macOS is not that difficult. So I think it's my presentation is valid just because of this. What do I want? I want to learn to load kernel code. As I told you, I like the kernel, and I want to load it as when I want and why, for whatever reasons I want to do it. Is this a problem? Apple introduced code signing in the kernel. They started with Mavericks. This feature was introduced in Mavericks. It was not a fatal exception, so you could load the kernel extensions. It will complain that saying that the kernel extension is not code signed. This code is probably bad, but I will load it anyway. This is comprehensible because they are introducing a new feature. Apple likes to do things in a smooth way. They don't want to break old stuff, so they do this. In Yosemite, they finally made this a fatal exception. If you try to load kernel code that is not code signed, the normal applications will refuse to load this code. These are the conditions, or some of the conditions, for the code to not be loaded. If there's no code signature, it will not load it. If it's invalid, if, for example, if you patch 1 byte, it will break the code signature and not load it. There was a nice trick that you could use with extensions. You could use, instead of your own identifier, your bundle identifier, you could use com.apple. The advantage of this is that this extension, your kernel extension, will be loaded very early in the system. For example, all the sandbox and other modules use this, so they are loaded very fast and very early in the system, which makes sense because you want to have these features, security features, loaded as soon as possible. I was using this trick, for example, for my stuff for the company I was working for, because we wanted to develop, to start our kernel extension as soon as possible. You cannot choose anymore because there's a check that sees if the certificate is signed with the Apple certificate, it's okay. If it's not, refuse everything signed with com.apple. What are the solutions for this? You can steal or buy a code signing certificate. This is the major problem of code signing. If you are selling code signing certificates, you can buy a new one. It costs you $99 US dollars, and an excuse to Apple. You can say them, I want to develop a security solution. One trick is never tell them that you want to develop a test, because if you are doing some tests, they will say no. But if you tell them, yeah, I'm developing a security product, then it's okay. You can use this parameter, the KX dev mode equal to 1. It basically removes the security feature out of your system. You probably don't want to do this. You can use if-I attacks. You had Snare presentation a few years ago at SyScan'. You had the Thunderstrike presentation at CCC. Basically, you are booting or you are attacking the system very early, so you control the whole code in the system. You can do whatever you want. And what I'm going to focus today, you can attack the user lane daemons. I'm going to show you what is this. You can exploit kernel vulnerabilities. I will exploit one kernel vulnerability that is still alive. And you can abuse the features of OS X, whatever is at hand. User lane daemons. So let's start or continue Stefan's presentation. It seems that Apple has no idea what they are building. I like this image. I had to find an excuse to use it, so let's show why. Where are the code signing certificates made? They are made in this daemon, KXD, which is also responsible for loading, for processing the requests when you want to load the kernel extension. If you use the kxload command, for example, to manually load an extension, it sends a request to this daemon, and this daemon will process and ask the kernel to load the kernel extension. It is running in ring tree, so it runs as root, and it's, for my pleasure, it's responsible for the code signature checks. So you have a problem. You have something running in ring tree, which is a lower privilege, trying to, oops, see, security. You have something running on ring tree, trying to check code that goes to a higher privilege, ring 0. This doesn't make any sense. For example, in Microsoft, you have the code checks on ring 0. It makes sense that if you want to load kernel code, you have to check that code at the same privilege. So what you can do, you just need to, if you have root, you can patch or can attack any daemon you want running as root. You attach to that daemon, or you can patch at disk. You can do this very dynamically without using a disk patch. You need to find that function, sec static code check validity, and if you come from the cracking scene, you just need to patch the return value, put it at 0, and that's it. You can load whatever code you want. I'm writing the rootkits book. I have some code that does this dynamically. It's very easy. You just need to find the symbol, this symbol, you patch it, and that's it. And after you load your kernel extension, that's it. So you really need 2 bytes, 3 bytes, 4 byte patches. The funny thing is that I wrote about this 2 years ago. It wasn't this very specific attack. At the time, I was just attacking Mavericks because it wasn't a fatal exception. What I was patching was the warning, because if the kernel extension was not signed, the user would get a warning saying, this kernel extension is not code signing, but I will load it anyway. So I was doing the same. I was patching that message. The user, you would not get anything. But the problem is still the same. The checks are still made in the daemon instead of being done in the kernel. So this is the conclusion. Apple, they don't know what they are doing. I have no idea why they did this. It doesn't make any sense. If it's not a security feature, then I don't know why they are implementing this. So I could end my talk here, because we just need to patch these bytes, and that's it. All the security of your kernel extensions on your Macs, it's dead. There's nothing else to do it. But as I like to develop things, let's show you really fun stuff. I like this cartoon a lot. It says a lot of this industry. You can put everything in your network. In the end, as you saw if you were here at the last presentation, the human element is always the weakest element in the chain. So let's exploit kernel vulnerabilities. I'm interested in any vulnerability, in any kind of vulnerability that allows you to write anywhere in the kernel. There's also the kernel task port. If you get the kernel task port, you can do whatever you want. This is because of the design of Mac. There's also another port, which is the host privilege port. It's even more powerful because it controls the system. If you can get one of these ports with a vulnerability or something, you can control the system. The reason for this is that every process in OS X, in Mac, in its design is represented by a task. The kernel itself is another task, and you can think about it as the PID0 in the system. Before the Snow Leopard, you could access the kernel task port by using this function, task for PID, and you use the PID0, which was the kernel, and that's it. The only restriction for this was running code as root. They fixed this. There was a FRAC article with this, developing how to use this. Apple finally patched this. You can see this, the check, because if the request is with PID0, it will refuse and not return the port. Last year, 2 Taiwanese researchers, Pan and TT, presented a vulnerability, an interesting vulnerability at Black Hat Asia, which is the processor set tasks vulnerability. Basically, this is a function that returns all the tasks in the system, including the kernel. The funny thing is that I had seen this vulnerability at this book, macOS and iOS internals book. At the time, I didn't pay attention for it. When they presented the vulnerability, this made a ring in my brain, and I went, okay, to check the book. Yeah, it's here. Okay, the vulnerability was there in plain sight, which is really fun. What allows you is to get the kernel task port. So it has the same result as the task for PID function, and it's still unpatched. This is the function. It basically goes to another function, which returns, starts iterating over the tasks on the system, and returns the port. The funny stuff is that you have a define there, define secure kernel. What is secure kernel for? It's from iOS. So Apple knows this bug. They patch it in iOS because it's defined as a secure kernel. In OS X, they don't care. They leave it open. This is the way to get that port. It's very easy. You just need to get the host port. This is one of the reasons why you need root access, because you need the host port and you can get that. If you could, for example, leak the host port from a vulnerability as a normal user, you wouldn't need a root user. After that, you just need to get the first element of the array because it's guaranteed to be the kernel task port. As I told you, this vulnerability is still not patched. If you try this on the latest Yosemite 10.10.2 or even on the latest betas, I didn't try with the real latest beta, but it's probably still there. It's still not patched. So Yosemite is as powerful as it looks, but it's also as vulnerable as it looks. As I told you, they know this bug. The funny thing is that, again, the funny thing is that I tried to patch this bug because it's a bug and it's a very powerful bug, and there are no side effects on the machines. If you try to patch it, you can use, for example, a kernel extension or directly patch your kernel. Your machine still works. I didn't add any side effect. So this is, again, really stupid stuff from Apple. Stefan has shown you how they do it. They take 2 years to patch bugs, whatever. Hopefully, finally this time, I will convince them to patch this. So let's go to the funny stuff, how to exploit this. What can we do with the task board? We can allocate kernel memory. There are kernel functions to do this. We can read kernel memory, and we can write and modify any writable memory. By writable memory, I mean writable pages, because there are some pages that are protected. Those pages are the kernel code. They make it read-only. There are also some read-only data sections. For example, the system call table is protected into this because it would be, or before you could just write the system call table easily. And we cannot execute code. We have access to the task board, so we have to find a way to execute code. What are the kernel obstacles that I'm talking about? As I told you, there is a FRAC article that develops on the task for PIT0, but it's not applicable anymore to latest versions because there are some protections. What are these protections? The kernel code is made read-only by changing the pages directly, the page protection. This means, for example, that you cannot use the Mac VM protect function to change the page. If you try it, the function returns OK, but the page continues read-only because the function doesn't have access to the page level. It's on a different level, so you cannot use this function. Also, some data sections, as I told you, are made read-only. You cannot modify the tables, the system call tables, the max trap tables. This feature was finally introduced in Mountain Lion. I'm not sure in Linux, it's like a couple of years ago they made this change. Apple took some time to make the same change. You could do one very interesting trick, which is, okay, the table itself is not readable, but there's a pointer that is readable to the table. So you just need to change that pointer that is writable, and you can have a shadow table easily by passing everything. Apple finally made some sense out of this, and they moved most of those pointers. There is this section, the GOT section, which contains most of those pointers. This section is writable, so you just need to find this section, modify whichever point you want, and that's it. In Yosemite, if you check Yosemite source code and binary, they move out of most of this stuff, so you cannot use this trick anymore. This is how they make the data pages. They also remove or set the pages as not executable. So this is normal protections. You know, or you probably know that we can bypass this protection. You just need to disable the write bits in the CR0 register. The thing is that we need code execution. So we have like a bit of a chicken and egg problem. We cannot execute code, but we want to execute code. If we can disable the CR0, then we can do whatever we want to the kernel code pages. Another obstacle, kernel ASLR. In macOS, you have a system call, kas_info. If you use this call, it will give you back the kernel slide. Obviously, for security reasons, this is disabled in iOS. It doesn't make any sense to have the same function in OS X, because probably the excuse for this is that the developers might need to know this function. Okay, then put a setting. Instead of making this default available, if the developer wants to make this, force him to use a boot parameter or something to have this syscall active. You can use infoleaks, normal exploitation stuff. You can use something else. I'm not talking about this. I wrote another way to get the kernel ASLR with this bug, essentially you just need to check the memory regions, you subtract the value, and you can find easily the kernel. So I want to execute kernel code. As I told you, we cannot modify the kernel code. If we could modify it, we just need to write somewhere and that's it. We can load our rootkit. We can leverage the system calls by overwriting the tables. In Maverick, this is okay. You can just use the shadow table, modify the pointer, and that's it. One potential solution for this would be the kernel extensions. You have many kernel extensions loaded by default, but they are deep protected. If you check the headers of the kernel extensions, you can see that they are writable, so they don't have the same read protection. The thing is that most of kernel extensions are loaded from a cache. And if you go see the code that processes the cache, it will make the pages also read-only. So you cannot abuse this for doing code execution. What is the solution? One good solution is DKOM, direct kernel object manipulation. We just need to find a writable data structure that will lead to code execution. We just need a small shell code, for example, to disable the CR0 protection. If we have something that has a very restricted space, shell code to disable CR0 is a couple of bytes, less than 10 bytes or something, or we can execute more complex code. I will execute more complex code, just load all the code, all the rootkit code and execute it. What is the target for this? Trusted BSD. If you know me, you know that I like a lot trusted BSD. I sent my slides to Stefan for review and he told me, yeah, trusted BSD again. There is a good reason for this. First, it allows us to create very stable stuff. We can write its data structures easily without landing into stability problems. We don't need, for example, locks or anything else. So it's a very nice target. And because of its design, it needs to be writable. I'm not sure if this is going to hold in the future because Apple is closing this. If you look at the kernel, they have a note saying that this is closed, this is private, don't use this anymore. I'm not sure if with this change they can make this, they can remove the writable feature of this. They can load the kernel extensions that they need that are based this on the sandbox, the code signing, and so on. They can make those, load those, and then close the data structures. So let's see what the future reserves for us. As I told you, this is a very interesting policy. You can do a lot of stuff on your system. You have many hooks available, and each policy configures the hooks that it's interested in listening to. The great advantage, as I told you, is that policies can be added and removed in a dynamic way. All the data structures are writable. It has even good stuff because it allocates some arrays that we are going to need. They are pre-allocated, so we don't need to get into very confusing stuff. And it leads to code execution because basically you set hooks, you get the callbacks, and that's it. So this is very easy to use for code execution. How? We just need to add a new policy. We need a single hook. We don't need to make a very complex policy. We just want to execute, start execution on a function. We point that hook to our rootkit entry point, and that's it. After that, it's rootkit code that is running, and we can do whatever. And then we call the function that we hook to start the rootkit. So we load the rootkit into kernel memory. We know that a certain function will trigger the rootkit. We start that function, and that's it. So 10 steps to victory. It's a bit more complicated, but the 10 steps give you a good overview. We need the kernel test port. This is using the vulnerability. We need to find the kernel ASLR, which is not very difficult. We need to compute the rootkit size because we need to allocate memory, also not very difficult. We need to allocate the kernel memory or find free space. Both solutions work. Then we copy the rootkit to kernel memory. We change memory protections because if it's allocated memory, by default it's not executable. We need to fix the symbols. I will show you why. Then we need to install a new policy and execute the policy. To get the kernel test port, It's very easy, I've shown you, and there's nothing special about this. To find the kernel SLR slide, let's go the easy way. If there's a syscall, we use the syscall. Because it's a 64 bits and I only work now with 64-bit kernels because 32 bits it's dead for Apple. You just need to use the syscall construct Unix, which is basically a macro that sets 1 bit for 64-bit syscalls, nothing difficult. To compute the root key size, there's a trick. Stefan was talking about the VM size and file size fields from the Mac VM. You should use the virtual memory size because they can be different. The file size usually is smaller or equal than the virtual memory size, usually because of alignment reasons. So just use the VM size, parse the rootkit, use the VM size, and that's it. You get the final size of the rootkit. To allocate kernel memory, you can use this function, Mac VM allocate. This function is used also in userland because the first parameter is the task where you want to allocate memory. We are not very fancy about where we want to allocate memory. We can allocate memory anywhere in the kernel. We just want a new memory on the kernel. Are there any problems of using this function? Yes, there are. The allocated memory is not wired. So when you try to, you allocate this memory, the kernel returns a pointer for this memory. You copy the stuff to the kernel, and when you try to use it, what you get? Page faults. Why? Because the memory is not whole paged in. A few pages are copied to the kernel, but the remaining pages are still swapped out, and this results in page faults because you are running the kernel code, and the page fault handler will not do it, will not handle it, and it will crash. What is the solution? It's very easy. The first time I was trying to find different solutions, trying to copy the memory, trying to force, trying to read the memory, didn't work. There is a function, Mac VM wire. What this function makes is this memory wired. So you allocate memory, and then you tell the kernel, make this memory wired, make this memory permanent, which is the same as the kernel memory, and this solves the problem. The only trick that you need to care about this function is that you need to set the final memory protection first. So the steps is you write the memory you write whatever you want to the kernel, you set the final protection, in this case is VM protect all to make the memory executable, writable, and readable, and then you say that memory, I want it to make it wired, and you use the same protection as you set before. If you use this trick, memory is wired, no more kernel panics. To copy the rootkits, use also another function, Mac VM write. This is also another userland function, uses the same task. This is the reason why we need the task port. If we have the task port, we can use all the Mac VM functions. You copy each segment because we are mapping ourselves. So this time you use the file size segments. If you use the VM size, if they are different, you'll overwrite with bad data. So you get the file size, you copy the data. You don't care about the remaining. If there's a difference, you don't care. It's not your problem. As long everything is set correctly, is mapped correctly, you are okay. To change memory protections, use Mac VM protect. You fix some areas that were not executable to executable. You probably want to, for example, set data not executable. It depends on either you want to confuse the volatility guys or any memory analysis, any forensic analysis. It's not important as long as it's executable, you're okay. Again, use the virtual memory size because this is the memory that is mapped and the final value, so you need to use this. The funny stuff. Fix external symbols. The kernel extensions code is pi because of kernel ASLR. If it wasn't position independent, then you would have to fix everything and so on. So we don't need to worry about that code. Everything is correctly set on the code, but we need to worry about the external symbols. Because we are not using the default interfaces, there is no kernel linker doing that work for us. So what we do, we implement ourselves a small kernel linker. How difficult is this? It's very easy. We have the same information that the kernel linker use. We have the relocation tables on our rootkit header information. We need the information from those two commands, lcdi symtab and lc symtab. Every information that you need is there. There are 10 different types of relocations. The first time I saw this, okay, this is going to be too complicated. I have too many cases to process. This is going to be boring. So as a good economist, I did a program, a small utility, to gather the data, process all the kernel extensions on the system, and you only have 2 types of relocations. This makes our work a lot easier. There are 2 types, the reloc and sign. This is used for RIP relative addresses. So basically, normal RIP relative addressing. You have the offset to the function computed against the current instruction pointer. And you have the reloc branch, which are absolute addresses. You tell the function or whatever, the symbol, it can be found at this address. These are the ones that are very easy to fix, because you just need to find the target address and set it. The external are the symbols from the KPIs, for example, string functions and so on. These are available from the kernel library. You have the local, which are usually strings, local strings, and some local kernel accession symbols, such as the start function and some other stuff. Not very important. As long as you fix it, you're okay. To fix it, you just need to process the header information. You find where the information is. You extract the symbol. There's a trick, which is you need to find the number, because the information, you don't need to process or you don't need to encode where each symbol is. So you have on the tables the information about the symbol number. For example, if string copy is the first symbol, and if you are using string copy in many places, you'll have 1111. So you need to find what is the number, which number that function is, and that's very easy to find. I'm going to release the source code so you can see this. And then you need to solve to find where that symbol is in the kernel, and then you fix the table yourself. This is the code that fixes the branch, the ones that are relative. If you see, I left this code on purpose. This was an initial version of my code. The RIP offset is just 32 bits. What is the problem? If you do your development in a VM, you are probably using like 2 gigabytes memory for the VM, it's enough. And in that case, the location, because we are selecting anywhere on the kernel, your location is probably guaranteed to fit on the offset. But this code you can overflow, and the offset can be wrong, because it might not be possible to fit in the 32-bit offset. I found this when I tested this in a real machine with a lot of memory, and it started crashing, and I wasn't paying attention, and then, yeah, I finally found where it was my code using the offset. So, well, how do you solve this? It's easy. It's very easy. You just need to allocate a trampoline island. You can reserve the space on your rootkit, so you redirect that to your code, or you can allocate new memory for this, because it doesn't matter, or unless you are really unlucky and the memory is allocated off the 32-bit displacement, then you can allocate the island and you put the island. The advantage of the island is that you can see, as you can see in my code, you can obfuscate the symbols. For example, you can put some XOR or some more complicated stuff. You obfuscate the symbols, and if someone dumps your code, they will need to solve, for example, all the symbols. So it's not directly, you cannot see directly which symbols are you using. So it gives more work for forensics. This is the code about the absolute branches. This is very easy. You just need to find the address, and you write the value, and that's it. You don't need offsets, so it's very easy to solve. This is about the local relocations. Basically, they are all unsigned, so no much work with this. Trusted B policy. I'm not going to explain you Trusted BSD. If you were here last year, I explained this while drinking whiskey. Basically, you can see the slides later. It's very easy. There is a structure, Mac policy list. This is the core structure contains information about trusted BSD. Then it contains a pointer to an array of MAC policy conf. Each MAC policy conf is the configuration of each policy. What we want is to add a new policy here, and then the MAC policy ops structure contains the pointers for all the hooks available. Essentially, we create this, we create a structure, a MAC policy ops, we allocate that structure, and we select the hook where we want to install the rootkit entry point. So these are the steps. We need to allocate memory for a new structure, a MAC policy ops, also to the MAC policy conf. We don't need to worry about this array, that array on entries, because it's pre-allocated with 512 entries. So we just need to find the free entry. It's very easy because we can use the num loaded, and we have the index information on the structure on MAC policy list, so we can find the free position and put it there. And then we need to set the new policy, and that's it. The function that I'm using the task for PID. This is the easiest hook to use, because you can always use this function. You can do task for PID1 on the launch T process to start it. You can use any other hook. The advantage, you want a hook that is not very hot, so you don't want the rootkit to start many times. You can do this by setting diffuse, but it's easier to use this function. To find the rootkit entry point, you can hard code this stuff. Hard code gives you problems. You want your rootkit as stable as possible. It's very easy. You process the rootkit symbols table. You find this info, kmod info. This information is always available, and you want the entry point is in the field of the destructor of this symbol. So it's very easy. This is the code you process. You read your kernel rootkit. You read these commands, and you find the information, and you have the starting point. Nothing very complicated. One trick on the MAC policy conf. The MAC policy conf has some information about, for example, some strings about the module. Everything can be null or zero, so you don't need to tell forensic analyst, there is my rootkit, or this string is on memory. You can use this, for example, for setting some information, but it can be null. This is good. You could set a string inside the rootkit as a valid pointer, or you could allocate memory for this. But minimal work, as easy as possible, makes things stable. As I told you, the entries array is pre-allocated. You just need to find a free slot, use the number of loaded policies to get that position, and write right there. To set the new policy after everything is ready, you just increase the num loaded and the max index, and your policy is finally active. This is one of the reasons why it's very stable to mess with trusted BSD, because all the macros have checks, for example, for null values. If you have a null pointer or something, it will not execute. So you just need to modify this array, and the policy is finally active when you modify this. You could, for example, the first step, you could set num loaded and max index. As long as the other pointers are invalid or are null, everything would be okay and very stable. To start the rootkit, you just use the task for PID1. The advantage, or using 1, because the launch D process is the equivalent to init in Linux. So it's guaranteed to only exist. If you kill this process, or if it dies, the machine will die. And then you add a fuse to your rootkit. It's probably the first instruction that you want to execute. Set a variable that no further executions, because this function is used, for example, for PS or activity monitor or some other daemons. It's not very frequent, so you are not landing into a race that you want to win, but it's easier to add the fuse, and you don't want to avoid the execution of your rootkit. And this is the code starting and then doing the cleanup. To do the cleanup, you want to disable your policy. essentially, you need to do the inverse step. You decrease max index and num loaded. After you do that, the rootkit or the policy is not active anymore, and because your rootkit already started, and you are guaranteed to not have further executions. And you probably want to wipe memory. For example, you want to remove that structure, all those footprints, and just have the rootkit code on memory. Let me show you how this works. Let's see. Okay, this is a Mavericks installation. It has all the latest patches available for it. So, let me clean this, what I'm going to show you. The first version, this is the sample code. You cannot see anything. Bah. Okay, so I'm going to execute the version with the exploit from Ian, the one that still works. I just patched some stuff in the exploit because it required some Xcode tools, some developer tools. So I basically removed that requirement. I didn't fix the exploit. The exploit is one shot. If you try to run it again, it will crash the system. Immunity did that, but I didn't want to make that exploit even more reliable than it is. So the exploit is running as normal user, non-privileged user, and it's executed, and the rootkit code is executed. What did I execute? I executed one of my code that is used for anti-debugging, anti-debugging, which is this utility. So I'm going to connect the kernel extension. It's connected, so it means that the rootkit code, this code is loaded into the kernel. And now, let me see. So this is GDB. This is a small program to test if the anti-debugging is active or no. Right now, there are no flags, no anti-debugging active. So if you run the program, it will alert you, a debugger is found, so there is no anti-debugging active. Now we activate this, run, no debugger found. So the kernel code is running without any problems. It was executed from a normal user using the exploit to get root access, and everything is stable. Also, this code is really fun because it allows you to get remote rootkits, to load remote code. Because you are just writing a buffer to kernel memory, you can get this buffer from anywhere you want. You can do this via HTTP, HTTPS, whatever other channel you want. So this is a remote rootkit. It's hosted on my website. It's just an hello world. Do I have network? Not yet. Okay. So it's downloading the code from the internet. It loads again. If you notice, I'm loading again more code on top of the other code. So the code is really stable. You can load as many kernel payloads you want in the same session. I never had problems with it. And if you can see, it's loaded the rootkit from a remote website. So this is really nice feature of this. Let's continue. My favorite feature or my favorite technique for loading rootkits. I call it the disguised devkmm. If you come from Linux, you know that this device used to exist in Linux. Now it's protected. It also exists in OS X. The thing is that it's not activated by default. You need to set a boot option to use this. You can set it by using the NVRAM utilities, or you can edit this configuration file and set the option. So what I'm abusing, there is a very nice kernel extension, Apple AHW Access. It was introduced in Mavericks, and what it allows you to read and write every bit of physical memory available on your system. The only protection that it has is root. So if you are root, you can communicate with this kernel extension and read and write to the whole system. It's not, you cannot use, for example, a buffer. You need to split this because you can only read or write in 1, 2, 4, and 8 bytes. So you need to send the requests. You need to send each request to the kernel extension. This is not very difficult. It takes, it's a bit more slow than the other technique, but it's like a few seconds to process, to read memory, to find the kernel, for example. So it's acceptable. So the first time I saw this, I was like, what the fuck? Why does this exist, and why it has no protection? This was first reported by this user at an Hackintosh forum when Mavericks was released. I read the post. The first time, it didn't click on my mind that I can use this for rootkits. And the reason was that the guy was talking, oh, this is not very stable. It can lead to kernel crashes. So my brain, if it's crashable or if it can lead to crashes, it doesn't make any sense. When I was developing the first technique, then finally it made click. Okay, I can use the same techniques with this feature, and I can probably make this work with kernel rootkits. What's the reason of this kernel extension? My guess is that they replaced the Apple profile. The Apple profile framework replaced SHUD. SHUD was basically a framework to do diagnostic, for example, performance stuff and other stuff. It was a kernel extension, and Apple converted to a private framework. The only this framework, April Profile Family Framework, is the only framework or the only code that you have in your system that uses this extension. So I guess this extension was introduced to keep the communication with the kernel, because these profile tools need to communicate with the kernel, so they need a way to go there. And I guess this is the extension. I don't know, Apple has no documentation about this, so it's only a guess. As usual, as Stefan told you, they don't talk to people. Everything is a secret, so we don't know. What can we do with this function? We can read and write. I put there almost every single bit of memory available. The reason why this is true in a VM, because you don't have any mapped hardware. In a physical machine, you have some mapped hardware, PCI and all that stuff in some memory regions. And if you try to read it, it will generate machine exceptions and crash. But we are okay with that. There's a nice trick to bypass that and to work around. We can also bypass all the read-only protections that I told you about, because we are reading and writing directly from physical memory. We don't care about the page protections. We can write to the kernel easily. What we cannot do with this function? We cannot allocate memory, because we are only read and writing. This is the only thing we can do. We cannot change memory protections, and we cannot execute code in a direct way once again. This is how you communicate with the function. It's basically an IO kit service. You connect to it, and you then process the requests. Let me skip this. It's not very important. It just have a structure, HW request, where you send the size, the address, and the data that you want to read or to read to, and the data that you want to write to. Then you use the IO connect call struct method. Use the 0 for reads and 1 for writes. You can say it's not very difficult. If you want to write, you just copy the data that you want to write to the structure, and then you send the request. If you want to read, you send the addresses and the size that you want to read, and then in the return structure, you get the data in the data field. So not very complicated. How to exploit this? The main step that we need to find a way to copy the rootkit to kernel memory, because we cannot allocate. We need to find a way or a free space to do this. We need to fix relocations. Right now, this is not a difficult step, because we already know how to do it. The only difference is how we write to memory, nothing very difficult. And we need to start the rootkit. This time I will not use trusted BSD, just because it's a bit more complicated, and we can do easier things. For example, we can write the system call, because this time we don't have to deal with the read protections. So the main problem is to find memory. We can find already allocated free space. For example, you have usually free space in the headers. The kernel header alignment space usually is big enough for a rootkit. At least is always, I've never seen it not enough, for example, for a small shell code. You can also use the kernel extensions alignment space. You can use a kernel function, for example, NFS function. If you know your target doesn't use NFS, never, you can use one of those functions. There are many other functions that are really with low usage on macOS, so you can use those functions and put the code there. Or you can allocate memory via shellcode, which is what I'm going to do. To do code execution, I told you you can add a new syscall or mactrap or overwrite another syscall. You don't need to overwrite because there's free space. You can add a new trusted BA policy. It's more or less the same technique. Instead of allocating memory, you just need to find the free space to put the structures and set the pointers. You can hook a kernel function. You can put the code and then execute the function. So it's very easy. In this scenario, it's very easy to do it. Again, the 10 steps to victory. The first steps are more or less. The step number 3, we need to find where the kernel is because we want to process the kernel. Then everything else is more or less the same. This is the same. You probably want to find the amount of available memory in your system because you don't want to read out of bounds. Because if you read out of bounds, you will crash the machine. So the first thing that you do, you find the maximum memory available on the system. It's very easy. You just use a sysctl or there are other functions. You get the maximum memory and you have the bound. 10. To find the kernel. There are two solutions. You can read from 0 till the end of the memory. As I told you, this doesn't work in a physical machine because you are going to land in machine exceptions. What is the smart solution? You can read the kernel address by just clearing the first 32 bits. The problem is that there is a direct mapping between the virtual address and the physical address. So if you clear the first 32 bits, you get the physical address. The first person that I know that talked about this was WinowCM. She told you about the same problem in iOS. There's a post where she talks about this, where there's the mapping, the same one-to-one mapping between the virtual address and the physical address. This is valid for the kernel. It's not valid for example, if for other stuff in the kernel, but for the kernel is, so this is what we want. So the trick is you read the address, the kernel address, from the disk image, then you add the kernel SLR slide. We got it from the system call. You just clear the first 32 bits and that's it. You know where the kernel is in the physical memory. The brute force solution is to read from 0, but this needs some work. You need to avoid the mapped memory. We'll have to skip this. This is to find the kernel. A simple trick if you do from 0 to end. There's a very interesting difference. The kernel headers in memory, they always contain the kernel ASLR slide. And if you read from the disk, you can find, if you find the comment, you can try to brute force. You find the kernel header, you do some tests. It's very easy to see if it's the kernel. You make the difference and you have the kernel ASLR slide, and you can be sure that it's the kernel image. Is it the same? Okay, to allocate kernel memory. I told you, you can use the alignment space between the text and the data segments in the kernel. That memory is executable because the header itself is executable, so it's good for us. It's usually big enough. In Yosemite, you can put 100K rootkit there, which is huge for a rootkit. It's not enough in Mountain Lion, unless the rootkit is very small, or you get, for example, a bootstrap rootkit that it will load the next payloads from disk. You cannot use this trick with kernel extension headers because they are not wired. So if you try to write data there, you'll get a page fault. What is the easiest solution? You just need to write a small shell code to the kernel headers, use that space or some other function, and then you execute that shell code. There's a trick. Use this function, kmem alloc config. What is the advantage? This function is guaranteed to allocate continuous physical memory. If you could use the normal functions, macvm allocate, for example. The problem is that you don't have any guarantee that there's a continuous physical memory allocated to you. So we can only write to physical memory. What you need to convert, you need to find where the physical memory, where the mapping is for each page. It's too much work. There is this function. It's much easier to use. So use this function, you get the memory, and that's it. You can see there are some small tricks because you need to get the addresses back. You can only read the physical address. One trick that I use, I write to a known place in the kernel that you are guaranteed to not landing into problems. These are some pointers, the constructors of the kernel. They are not used anymore. You put there and you remove that. This is the same stuff. You just need to copy each segment. You don't worry about wired memory. It's guaranteed to be wired. To fix the symbols, it's the same stuff. You just use the different function to write to memory. To start code execution. 1 minute. You need to modify a system call entry. You locate a system call, you overwrite a system call, and you use it for starting the rootkit. You have to skip this. This is in case you use the header. Basically, you have a function to disable the CR0 because you have multi-core system. You want that code to execute in all the cores, else you're landing into problems. Let me show you quickly the demo. So this is the presentation machine. So if this goes down, I failed. Hopefully, the last time it didn't. So I'm loading a small test code. Oops. So it failed. I don't have time to fix this. I will show you later if you want this working. Conclusions. OS X security, or I hope that I convinced you that, don't tell anyone, it's crap. Total crap. Why? Hopefully I've shown you that KX code signing is useless. Don't trust it as a security measure. I have seen some AV companies, or at least one, in a blog post telling, yeah, you can trust there's KX code signing to protect you. I have shown you that that's not true. If it's not a security feature, why the hell does it even exist? I guess it's just a measure to put developers, not let every developer load code. I don't know why the hell they implemented this. It doesn't make any sense. At least they could try as Microsoft to make it really good. There's no official product end of life on Apple. If you come from an enterprise network, this is a mess because you get Usemite or the latest version, and Apple doesn't say anything about the previous versions. They released some patches, for example, for Mavericks, but they released only after a couple of months. So Usemite had those bugs patched. Mavericks and previous version didn't. So it's a mess. And even if you get the patches, you still are vulnerable because, as Stefan's shown you and I did, Apple doesn't know how to patch stuff. They leave you vulnerable, and so it doesn't make any sense. So my idea is that Apple product strategy is reactive, not proactive, if they have any strategy at all. This is the same conclusion as Stefan. I don't think they have any strategy. I hope they start changing this. You can find the source code and the slides. The source code for both.
You should have just presented the last slide.
This is the last slide. Oh, and thank you for the last SyScan and to everyone that made it possible. My contact information, feel free to annoy me. Have fun.
Okay, Pedro, thank you.